Hello and thank you for coming. My name is Mark McDonald and I'm a PhD student at Brigham Young University. Today I'm going to be talking about my research in steering colloids using chemical gradients. One interesting thing about colloids is they can make dynamic materials, or materials that change shape with time. An interesting example of a dynamic material is seen in the chameleon. Chameleons have crystal structures in their cells that reflect certain wavelengths of light and give the chameleon skin its color. When the chameleon gets excited, it releases chemicals that cause the crystal structures to change lattice spacing, and so the chameleon's skin changes color. Nature creates dynamic materials using a complex system of feedback control of chemical reactions. We want to do something similar. Our paradigm is based on electrokinetic steering research. In electrokinetic particle steering, a colloidal particle is placed in a microfluidic device surrounded by electrodes that change their voltage with time to steer the particle on a target path. We chose a circular trajectory as our target path because it's a simple example of a dynamic trajectory because the velocity is constantly changing with time. To adapt this electrokinetic steering to chemical control, we replaced each of the electrodes with a highly controllable chemical reaction. So we tell it what the reaction needs to be, and the reaction creates a solute that diffuses to the location of the particle and causes it to move. One of the problems with chemical control is that diffusion has a significant time delay. It takes a long time between when the reaction happens and when its effects reach the location of the particle. We solved this problem using model predictive control, which we'll go into a little more later. Our simulations are similar to Brownian dynamics. We start with an ordinary Brownian dynamics equation, except there's no interaction term between particles, because there's only a single colloidal particle. However, there is an interaction between the particle and the solute. The gradient in the concentration of the solute exerts a diffusiophoretic force on the particle and causes it to move. So this term is the diffusiophoretic force term. This diffusiophoretic force term is equal to the drift velocity, and when we assume that the solute is dilute and non-ionic, it's equal to a constant mu times the gradient and the concentration of the solute. So if we know the concentration field, we know the dynamics of the particle. We solved for the concentration using a finite difference method over a grid of points. Now I'm going to give some background on model predictive control. Model predictive control uses a model of a process to predict the future behavior. We chose model predictive control because it deals with three problems. The first is time delay. The diffusion causes a significant time delay. The second was nonlinearity. This problem is highly nonlinear, and it makes it difficult to solve using linear control techniques. The third is constraints. We don't want our reactions to be negative, so we constrained the values to be positive. In model predictive control, previous measurements, these are the blue dots, and previous inputs, which are the blue lines on the bottom, are used and fed into a model of the process to predict future outputs, which are the orange dots. An optimization algorithm calculates the optimal future inputs to use to move the orange dots onto the green line, the target trajectory. Model predictive control requires three things: a model, a target, and an optimization algorithm. Our model was derived using the method of Green's functions. I won't go into the full derivation here, but I'd love to talk about it later. Briefly, the concentration at the location of the particle is found using a convolution of the diffusion Green's function and the function of the inputs to derive a sort of a time series model. Our target function came from the field of unmanned aerial vehicles, or drones, and it's a technique called a guidance vector field. A guidance vector field takes in a measurement of the particle's position and outputs a target vector to move it onto the stable path. We used a guidance vector field instead of a simpler target function because the time delay compounds with the stochastic motion of the particle and can move it far away from the trajectory we want. But the guidance vector field helps correct for that. For our optimization algorithm, we used nonlinear optimization, so we didn't have to lose information by linearizing the problem. We used an algorithm called trust region reflective. So let's see how it does. As you can see, there's a significant degree of Brownian motion. Around the outside, the four sources of the chemical reaction alternate releasing the solute to make sure that the particle is always moving up the gradient lines. Despite the Brownian motion, there is a little bit of error, but it looks like it does pretty well at reproducing the circular trajectory. For this simulation, we used a diffusion coefficient of the solute is the self-diffusion of water. The nominal radius of the particle is 1 micrometer, and the speed that it travels around is 1 micrometer per second, so the video is slightly sped up. The simulation I just showed was one that worked well, but sometimes it doesn't work that well. We found 3 rules that need to be met for the particle to accurately be able to reproduce the target trajectory. The first one is fast control. We need the controller to be fast enough. The second is a reasonable time delay. It's very difficult if the time delay is larger than you're able to deal with. And the third was we need a small degree of Brownian motion, so the Brownian motion doesn't have a chance to move the particle away from the desired trajectory too far. To quantify these rules, we looked at the timescales inherent to the system. I'll briefly go over 4 of them. The first is the control interval duration. This is the amount of time between loops in the model predictive controller. The second is the diffusion time of the solute, a measure of the time it takes the solute from when it's created to when it reaches the location of the particle. The third is the period of the trajectory, the amount of time it takes the particle to move around the circle. This is useful for comparing to the other timescales. And the fourth is the Brownian diffusion time of the particle. This is a measure of how long it takes Brownian motion to move the particle away from the desired trajectory. Now, applying these timescales to our 3 rules. For our first rule, fast control, we need the control interval duration to be smaller than the solute diffusion time. This isn't too hard to do as long as your computer is able to solve your model fast enough. You can normally set delta t to be small enough. Our second rule, we need a reasonable time delay. For this one, our solute diffusion time must be much smaller than the period of the trajectory. This provides a bound on what trajectories are possible. And our third rule, for Brownian motion to be small enough, we need the period of the trajectory to be much smaller than the Brownian diffusion time of the particle. This provides another bound on what trajectories are able to be dealt with. On this graph to the right is a summary of the trajectories that are possible. For a given circle radius, there's an upper bound provided by the time delay. Above this, for a velocity greater than this, the time delay is too great. A lower bound is provided by the Brownian motion. If your directed velocity is too small, then Brownian motion overcomes the guided trajectory. This blue line is for a smaller degree of Brownian motion. Anywhere in either of these 2 blue regions is possible. But for a larger degree of Brownian motion, it restricts the velocities even more. Only somewhere in this smaller blue triangle is possible. In conclusion, we used model predictive control of chemical gradients to steer a colloidal particle on a target path. And it worked, but sometimes it doesn't work. In order to be able to reproduce a target path, certain relationships between the timescales need to be met. These relationships will be important for designing future dynamic materials. For example, in this simulation is meant to represent a crystal structure changing lattice spacing. We applied our timescale relationships to make sure that it worked. And although there are still some problems to be solved, it looks like it has great prospects for the future. Thank you.